So here we have a very typical problem, and I'm going to do this one without numbers because I think some of you guys have expressed some stress about that. So they give us a few things. They give us the mass of the electron. You can consider that something we know. They know the charge of the electron. You can consider that something we know. They give us the length between the two parallel plates, and they give us the strength of the magnetic field. This is hooked up to a battery. It's a very terribly drawn battery, but whatever, it's Saturday. I do what I do. So we're going to try and find a few things out about this. Let's start with a basic question they like to ask it, which would be, so there's a couple ways we can approach this. First, let's talk about what's happening here. So we have a battery set up here, and that means that the positive end of the battery is here and the negative end is here. So this plate is going to have a lot of positive charge because the battery has essentially shuffled all the negative charge over here. Okay. What does that mean in terms of an electric field? Well, electric fields point away from positive toward negative. How do we know that? Because test charges, which is how we sort of figure out what electric fields do, are always positive, and positives want to get away from other positives and want to head toward negatives. Okay, I did not draw this uniform, but you're just going to have to accept it. Live with disappointment. Okay, so you're like, well, wait a minute. If the electric field is going to the left, doesn't that mean that this little particle here is going to be stuck there because it's a negative charge? Well, no. Remember that negative charges go the opposite direction of electric field lines. They fight the electric field lines. They go the other way. So this little guy over here is going to want to go to the right. So we could actually, if we wanted to, we could approach this problem by finding the strength of the electric field using VED. Okay. And then if we wanted, once we knew the electric field strength, we could do, all right, force is equal to E times Q. We could do the force. And from force, we could use F is equal to MA and go after the acceleration. From acceleration, you could find out final velocity using your kinematic equations. That is, I feel like, the annoying way to solve this problem. The less annoying way, in my eyes, which not everybody has to agree with, is to use energy. Why do I think that? Energies are scalar, they're prettier, they're better dressed. There's lots of reasons. Okay, so we're starting over here, and right now this charge is got a negative charge. It wants to go toward the positive end. So you could think of it as having potential energy. Just like a ball that you hold up above the ground wants to go toward the ground, and so it has potential energy. This little charge here has potential energy. What is going to happen to that? Well, as it moves through here, it is going to gain kinetic energy. And if we knew that kinetic energy, we could find the velocity. All right, so if we can know the potential here, and we know it's going to lose its potential by the time it gets here, and it will all turn into kinetic, then we should be golden. So we start out, all right, what would be the potential energy at that point? Well, U is equal to, at this point, it's going to have, as it goes through this motion, it's going to have a change in voltage that should match the battery. Oops, I forgot to give you the voltage on the battery. It's that. Good, it's V. Everything's good. And the charge, so its potential energy should be equal to the potential that's going to go through times the charge. And in this situation, we can't just leave it like that because they gave us some of this. They gave us the voltage on the battery, and the charge is the charge in electron, and then the charge on the electron was negative, so negative EQ. You may think for a second, like, wait a minute, that shouldn't be negative. Well, remember that as we are going through this, you are going from a position of low potential, because this is a negative end of the battery is hooked up there, to high potential. So essentially your change in potential was negative as well. So these guys are going to cancel out. So your change in potential was V times E. Yay! Okay, why am I cheering? Because all of this potential here will turn into kinetic by the time it gets to here. So we have now our kinetic energy, which is V times E. If you have kinetic energy, you can use m of the electron times the velocity squared divided by 2. And they asked us for that velocity, so we can do, oh, by the way, notice how I'm like being pretty here with my velocities. I'm trying to show that it's different than this truly strong, not pretty V. So I'm trying to show they're different. I realize that some of you have absolutely horrific handwriting and just making a V is a challenge, but if you can do that, it's nice. Try and make the capitals and the small ones different. So V times E 2 divided by m E equals V squared. And of course, I'm running out of room here. We want to square, take the square root of the opposite side. And Yahtzee, we've got it. To make your day better, here is a bunny that believes in you. It believes you can do these problems.